All right, let's jump right in. Today, we're going to take a look at a recent, kind of viral moment from pop culture, but we're going to use it to get our heads around something much, much bigger: how science actually works. You know, that tough, often misunderstood process that figures out if a new idea is truly groundbreaking or just plain wrong. So, where does this whole thing kick off? Well, it starts right here. The one and only Neil deGrasse Tyson, the astrophysicist, suddenly finds himself being talked about by actor Terrence Howard on, one of the biggest podcasts on the planet. But here's the thing. This whole story, it didn't just start in that podcast studio. Nope. To really get it, we got to go back about 8 years. And that really is the big question here, isn't it? What happens when a Hollywood star with a ton of passion decides to take on the entire world of physics? I mean, this isn't just a story about two celebrities. It's the perfect example of what happens when a brand new, really bold idea goes head to head with the time-tested, centuries-old process of how science figures things out. So to really understand what's going on now, we have to hit the rewind button. Because this public call-out, it's really just the latest piece of a puzzle that started with a private exchange almost a decade back. Okay, so picture this. 8 years ago, Terrence Howard, who, by the way, is genuinely passionate about science, sends Neil deGrasse Tyson this 36-page manuscript. It's filled with his own new theories about math and physics. Apparently, they had met briefly before, and Howard mentioned he was working on something he thought was a game changer. Now, this is where it gets really, really interesting. How did Tyson react? He didn't just toss it in the bin. Not at all. He actually treated it with total professional respect. He spent hours going through it line by line, marking it up with red ink, just like he would for a paper from any other scientist. He was, in essence, doing a peer review. And that whole exchange, it's the perfect setup for understanding two key ideas that are basically, well, they're like the immune system for science. They're what protect the entire field from ideas that sound amazing on the surface, but, just don't hold up when you really look at them. So first up is this thing called peer review. And look, it's easy to think of it as just being critical, but it's not about that. It's more like a collaborative stress test. It's literally the job of other experts to try and find the weak spots, to poke holes in your argument, to double-check your work. It's the exact opposite of an echo chamber, right? The whole point is to get to the truth, not just to make everyone feel good about their own ideas. And that brings us to the second big idea: the Dunning-Kruger effect. I'm sure you've seen this in action. Maybe you've even felt it yourself. It's that funny thing our brains do where knowing just a little bit about something really complicated can make you feel super confident, like you're an expert. You know just enough to think you're right, but you don't yet know enough to see how you might be wrong. Okay, so we've got these two ideas on the table: peer review and the Dunning-Kruger effect. Now let's actually look at what was in that manuscript. What were the claims? And more importantly, how did they hold up when they were put through that scientific stress test? Right out of the gate, the manuscript makes a huge, huge claim. I mean, we're talking about challenging the absolute bedrock of mathematics. The thesis was basically that there's this one loose thread, and if you pull it, the whole system we've built could just unravel. But here's the thing about math and science. For a rule to be a rule, it has to work every single time. No exceptions. And Tyson, well, he spotted an exception right away. Think about numbers between 0 and 1, like 0.64. The square root of 0.64 is 0.8, which is bigger. And poof, just like that, with one simple counterexample, the whole argument falls apart. That's a huge lesson, right? One exception can break the entire rule. The manuscript also brought up some historical figures, guys like Walter Russell and John Keeley, and kind of framed them as these misunderstood geniuses who were ahead of their time. But from a scientist's perspective, Tyson saw a major difference. Their ideas might have been fascinating, but they were missing the two non-negotiables of science. You have to be able to prove it with an experiment, and other people have to be able to get the same result. And this leads to a quote from Tyson's notes that just hits the nail on the head. It perfectly sums up how scientists think. It's not enough to just be misunderstood or have a radical idea. To really be a genius, to actually change the game, your idea has to be provable. It has to be testable. Anyone, anywhere, should be able to repeat your work and see for themselves. Okay, let's look at another one. It was a pretty simple thought experiment. You place a candle in front of a mirror. The claim was that a light meter would measure double the amount of light. Sounds plausible? Maybe. But when you actually apply the laws of physics, it just doesn't work. For one, no mirror is perfectly reflective, so you lose some light right there. And two, the reflection is farther away from the meter than the actual candle, so it's going to be dimmer. It's a simple physical fact you can go and test right now. So, after all this, you might be thinking, wow, science sounds really harsh and closed-minded. But that's not it at all. Actually, it's the complete opposite. This super tough skeptical process, that's exactly how the truly revolutionary ideas, the ones that change everything, finally get proven and accepted. I mean, take a look at continental drift. When Alfred Wegener first proposed it, people literally laughed him out of the room. They thought he was nuts. But then, over decades, the evidence started piling up. Scientists started mapping the ocean floor, they found matching fossils on continents thousands of miles apart, and slowly but surely this crazy idea became the undeniable, foundational truth of geology. And it's the same story with Einstein. You know, his theory of relativity, it was this mind-bending idea he published in a journal. But it was still just an idea on paper. It wasn't proven until 1919 when an astronomer actually went out during a solar eclipse and observed starlight bending around the sun, proving that gravity really could warp space, exactly like Einstein predicted. The idea needed evidence. So what's the big takeaway here? It's that science isn't just a big book of facts. It's a process. It's like an arena where new ideas have to fight to survive. The whole point isn't to defend the old stuff. It's to attack the new stuff from every possible angle to see if it holds up. And what's left standing is what we can call objective truth. And that's something really important for all of us to remember, especially now. The real debate happens in labs and scientific journals, not necessarily on social media. And it's really important to see that, in the end, Tyson's critique wasn't a personal attack. He even ended his notes by saying how beautiful and artistic the illustrations in the manuscript were. He said his bluntness was a sign of respect for all the energy and passion Howard had clearly put into it. See, he was going after the science, not the person, and that's a huge difference. Which kind of leaves us with one last thing to think about. When we're trying to figure out the universe, what's more important? An idea that feels beautiful and elegant, or an idea that you can actually prove? In the world of science, the ultimate goal is to find the ideas that are both. Thanks for digging into this with me, and never stop asking questions.